Hello students, let us start with module 5, image segmentation. This is the image processing where the methods whose inputs and outputs are images to the two methods in which the inputs are images but the outputs are attributes extracted from those images. Now we'll see what is segmentation. Segmentation is the process of partitioning an image into regions. Segmentation subdivides an image into its constituent regions or objects. The level of details to which the subdivision is carried out depends on the problem being solved. So that is, segmentation should stop when the object of or the region of interest in an application have been detected. Segmentation of non-trivial images is one of the most difficult tasks in image processing. Segmentation accuracy determines the eventual success or the failure of the computerized analysis procedures. Because of this reason, considerable means there is a requirement for the to improve the probability of accurate segmentation. In some situations, like industrial inspection, uh, at least once some measures of control over the environment typically is possible. The experienced image processing system designer invariably uh, can pay attention to such opportunities. In some other applications like autonomous target acquisition, the system designers has no control over the operating environment, and and the usual approach is to focus on selecting the type of sensors most likely to enhance the object of interest while reducing the contribution of irrelevant image details. A good example for this is infrared imaging for military applications, where to detect an object with strong heat signatures, such as equipments and troops which are in motion. Most segmentation algorithms are based on two basic properties. One is intensity values, that is discontinuities and similarities. In the first case, that is in the case of discontinuous, the approach is to partition an image based on abrupt changes, means random changes in the intensity, such as edges. The principal approach in the similarity category are based on the partitioning an image into regions that are similar according to a set of predefined criteria. So here groups of regions is nothing but a group of connected pixels with similar properties. So as we said that one is based on the discontinuities, and the second one is based on the similarity. So there are two approaches to segmentation. One is on similarity basis, it is called region segmentation. On abrupt changes, it is called edge segmentation. Now let us take an example here, where this here the first figure, this image figure shows a region of constant intensity superimposed on a dark background, also constant intensity. These two regions comprise the overall image region. And the second figure, and figure B, uh, shows the result of computing the boundary of inner region based on intensity discontinuous point on the inside, and outside the boundaries are black, that is zeros, because there are no discontinuities in the intensity in those regions. To segment this type of images, we have to assign one level, say white, to the pixels on or in interior to the interior to the boundary, and the another level, say let us take black, to all the pixels in exterior to the boundary. Now figures C, this figure shows the result of such procedure, whatever the procedure is said inside the boundaries and outside the boundaries, but let us take in black and white. So now we can see here, inside the boundaries it is made white, and outside the boundary it is made black. And the figure D, if a pixel is on, the prediction of the condition B, that is if the pixel is on or inside the boundary, label it as white, otherwise it is called black. Now the next three, whatever the next three, these one, 2 and 3, next three the figure E shows the result of computing the edges of this original image, and the figure F shows the result of dividing the original image into sub-regions of size 4 by 4. Each sub-region was then labeled white if the standard deviation of its pixels was positive. Now let us see the segmentation methods that are based on detecting sharp changes in intensity. The three types of image features in which we are interested in isolating isolated points, isolated points, lines, and edges. Edge pixels are pixels at which the intensity of an image function changes abruptly. Here, yeah, it just abruptly. And these are the set of connected edge points. Now the edge detectors are local image processing methods designed to detect edges. A line a line may be viewed as edge segment in which the intensity of the background on either sides of the line is either much higher or much lower than the intensity of the line pixels. So averaging, first taking the edges points, then averaging, then taking the local changes in the intensity that can be detected using derivatives, first derivative and second derivative. Or so derivatives of a digital function are defined in terms of differences. Uh, the various ways to approximate these differences is, first one is must be a zero in areas of constant intensity. Second one is must be non-zero at onset of an intensity step or a ramp. Must be non-zero at point along the intensity ramp. Similarly, we require an approximation used for second derivative, that is must be a zero in areas of constant intensity, must be non-zero at the onset and end of the intensity step or ramp, must be zero along the intensities of the ramp. Now let us understand this with an example. This is the figure which shows the which contains the various solid objects, lines, and a single noise point. You can see a single noise point. And the second figure shows the horizontal intensity profiles or the scan lines of the image approximately through its center, including the isolated point. The transition in the intensities between the solid objects and the background along the scan line shows two types of edges, that is ramp or a step, just ramp change or an S step change. Uh, transition involves thin objects such as lines, often are referred to as roof edges, and the figure C shows the simplification of the profiles with just enough points to make it possible for us to analyze numerically how the first and the second derivatives encounter a noise point or a line and edge objects. And this next in the simplified diagram, if you can see the simplified diagram, the transition in the ramp spans 4 pixels, whereas for the noise point is a single pixel. The line is a 3 pixel thickness, and the transition of the intensity taken intensity step take changes between adjacent pixels. The number of intensity levels was limited to 8. Now let us take the intensity levels, let us take to 8, that is nothing but from 0 to 7, so including 0 till 7, so 8 points are there. Now let us consider the first derivative is non-zero at the onset and along the entire intensity ramp, while the second derivative is non-zero only at the onset and the endpoints, because edges of the digital image resembles this type of transition. Now we can conclude that the first order derivative points produce thick edges, and the second derivative must much finer ones than the first one. So we can encounter isolated noise point. You can see the noise point here. This is the noise point. You can see the isolated noise point, and the magnitude of the response at the point is much stronger than the second than the first order derivative. Now let us understand. So here the image strips are taken, then fine, first derivative is nothing but from this point. From 5 it has become 4, therefore minus 1. From 4 it has become 3, minus 1. 3 it has become 2, minus 1. From 2 it has become minus 1. From 1 to 0 it is minus 1. 0 to 0, no change, 0. 0 to 0, no change. 0 to 6, therefore it is positive change of 6. 6 to 0, minus 6. 0 to 0, 0. 0 to 0, 0. 0 to 0, 0. 0 to 1, it is 1. 1 to 3, so it is a positive change of 2. Then 3 to 1, so it has reduced by minus 2. 1 to 0, it is minus 1. So in this way you have to fill the first derivative and also second derivative. So take one more derivative of the first one, that is nothing but differences you can take. Minus 1 to minus 1, it is 0. First one you have to take as it is. This minus 1 to 1, it is 0. Minus 1 to 1, it is 0. Minus 1 to 1 is 0. Minus 1 to 1 is 0. Minus 1 to 1 is 1, because it has changed from minus 1 to 0. 0 to 0 is 0. 0 to 6 is positive 6. Plus 6 to minus 6, it is reduced by minus 12. Minus 6 to 0, 12, and so on. Now here you can see the all the values have changed from 0 to 8 only. Here you can see an abrupt change, that is nothing but an isolated point. Here this point is called the, all the changes are either a ramp or a step. Here an abrupt change is there. This point is called isolated point or the noise point. Therefore, the first order derivative generally produces thicker edges in an image. Second derivative have a stronger response to the fine. Such thin lines isolated points and noise. The second derivatives produces a double edge response at this step and this one. The sign of the second derivative can be used to determine whether the transition into the edges is dark or dark to light. So here for computing purpose, the first and second derivative at every pixels in an image use a special filter of 3 by 3 filter mask, and the procedure is used for the sum, that is nothing but R is equal to W1, which is nothing but this W1 into Z1. So on this image, this point, whatever the mask is there is overlapped across the image, and Z1 is the pixel at that location where it is overlapping. W1 Z1. So R is equal to W1 Z1 plus W2 Z2 and so on, here till 9 points. Whatever the 9 points are there, till 9 points. So this is nothing but summation K, let us take it as K equal to 1 to 9 WK ZK. So this ZK is something intensity of the pixels whose spatial location corresponds to the location of the kth coefficient in the mask. So this is the mask, general mask of the size 3 by 3.